everyone. In this class, we'll be discussing this topic of linear elastic material, linear elasticity. And then the way we would proceed is first I will try to motivate why we are learning this subject of linear elasticity. And then we'll get into the mathematical details of how to move along. So let's see if we can proceed. So one of the first things is to sort of recap what we have done until now in this course. Until now, we have learnt about the strain displacement relationship, which is Eij is equal to half Ui comma j. So let me just so the strain displacement relations can be Eij equal to half Ui comma j plus Uj comma I. Then we have had the compatibility equations. Okay, so this is a strain displacement relation, then there is the compatibility relations, and then we have the equilibrium equations, which is sigma ij comma j plus fi equal to 0. So remember, there are these 6 strain displacement relations, just because E21 would be the same as E12. So we don't have 9 but 6 strain displacement relation. There were 6 compatibility equations whose purpose was to ensure that for a given arbitrarily given strain, the displacement should be single valued and continuous. And then finally we had the 3 equilibrium equations, which were basically trying to just say that an arbitrary point in a solid is in equilibrium for this overall solid to be in equilibrium. All these 3 relations were actually valid at one specific point. Okay, so all these 3 are valid at this one specific point. There was also a relationship about moment balance, but as you knew, all it did was just tell us that stress was symmetric. So it's not some sort of a new information, because the symmetry of stress is already implicit in this relation. Okay, now let's see. At this point, what are the things which we would want to know? If there was an external load on this solid, what are the things which we would want to know? We would want to know the 3 displacements components, we would want to know the 6 strain components, and we would want to know the 6 stress components, given the applied loading and the body force. Okay, body force is normally considered to be given, like the force of gravity. So the unknowns which you have are these 3 displacements, 6 strains, and 6 stresses. So they constitute exactly 15 unknowns. Now coming to the equations, you have the strain displacement relation true. You have the compatibility equations, but compatibility equations, remember, they don't actually add any new information. All they do is ensure that the strains must satisfy this relation for the displacements to be continuous in single values. So we don't actually count them. And then you have the 3 equilibrium equations. So you have 9 equations. Okay. So that's the logic behind this. And these compatibility equations, whether 6, and I mean, if you remember, we had also shown that they were actually 3. I think we had done that proof. They have only 3 independent relations, and they only ensure that the given strain field is the given displacement field is single valued and continuous. Okay, so this is not adding anything new. So the 6 strain displacement and 3 equilibrium equations are 9 equations, and you have 15 unknowns, and hence we have to now add some more information, perhaps a relationship between stress and strain. Okay, and that is where we want the material response to come in. Okay, so There are a few terms which I would just briefly go over, but perhaps you would know it from your earlier knowledge. The term constitutive relation is a relation or an equation. Constitutive equation, constitutive relation is the relation or equation which characterizes the physical properties of materials. Okay. Now in this particular case, it is normally the relationship between force and displacement or stress and strain. So a constitutive relation in our language, in our sort of subject, is the relationship between stress and strain. Now it can also be the stress depending on the strain rate, for example, okay, or the history of the loading and things like that. But because we are referring to only a linear elastic solid, the strain rate is not of significance. So whenever we are always working in this quasi-static uh, domain in which the strain rate is very small and hence negligible effect on the response of the material. So we would only refer to this as the constitutive relation or the stress strain constitutive relation. Do remember that say for a discussion on plasticity, you would require the relation between stress strain in terms of the strain rate as well. So rate is an important parameter many a times. If it's a rate dependent on rate independent plasticity, it's a different domain. Normally, if you have a viscoelastic material, then time definitely plays a role. So lucky for us, we don't have to get into those complications in this course. Yes, there is another subject and another day for something like that. We would want to discuss or focus on the simplest kind of behavior, which is called a linear elastic behavior. The reason why we would want to discuss this is because, first of all, its theory is well developed over the last 100 years or so, and hence it's a very rich literature to be available. Secondly, it is very easy to use in most of the materials of everyday life like metal, plastic, ceramic, wood, rock, concrete, and so on. Okay, as long as obviously the deformations are small, that's always there. And lastly, because this course is really built up from the fundamentals, and it's possible for us to use the known subjects by you, the audience of this course, to build up a theory to this subject. Okay, so that's why we are taking this particular example, and we are constraining ourselves to the linear elastic materials. And I will, by the end of this course, not end of this course, perhaps somewhere in the middle of this course, I will also tell you that why are we still learning 100-year-old theory. Okay, it has been used for 100 years and tons of decades have passed, and we continue using it. There are two very simple reasons for that, and we will see that as we learn this course. Not in this chapter for sure, but you will see that why everyone talks about linear elasticity and few people talk about plasticity or viscoelasticity and so on. Okay. So it has there are reasons for that which are not there in other subjects like plasticity and viscoelasticity. Okay. So you may have learned about this uniaxial test in which you have a sample like this, so-called a dog bone sample. You pull it from two different sides. So a uniaxial test, and then you would eventually want to plot the relationship between a uniaxial stress and strain. Okay, I do not want to discuss this a lot, but you must be aware that there is a proportional limit, okay, at which the initial linear response between strain and stress ends. Then there is an elastic limit. Elastic limit is that point beyond which, if you remove the load, it will not come back to zero strain. So elastic limit is practically that point where if you remove the load, it will come back to uh, zero strain. Okay, so this elastic limit can also be slightly in the non-linear region, but the point is still that if you remove it, it will come back to zero. So if the path of stress versus strain goes slightly like this, so if this is the elastic limit, despite the fact there is a small non-linear part over here compared to this linear part, still if you remove the load over here, it will come back to 0. But for if you take it further than this, then if you release the load, it will come back to say this place, which is not a 0 strain. So that's the elastic load. Proportional limit, as has been told, is the place where this linear elasticity works, and beyond this, this linear elasticity, this is the proportional limit, the linear proportionality between stress and strain ends. For most materials, the difference between elastic limit and the proportional limit is negligible, and hence you will only find only one of them reported, and they are interchangeably taken. But you should know the difference between the two. Okay. The third point is the so-called yield point. Okay, this is a case where large plastic deformation begins. So if you say have something like this, and you have large plastic deformation to go beyond this, this would be called the yield point. Okay, and you must have learned how it can be found out, and how it's not very clearly defined if you in a stress strain graph, and there are ways to find it 0.02%, sorry 2% and 5% yield strain, those sort of behaviors. You would know how to find all those things. Okay, but this is all how it looks like. And yield point, as you may be aware, is also used as a criteria for failure. If a material has yielded, meaning it has had a large plastic deformation or begins to have a large plastic deformation, then it is assumed to fail. So many of the failure theories are actually only considering the yield failure, not the final fracture where it breaks into two separate parts. Okay, so this is the topic about this. Now, one of the other things, as you know, is that a ductile material would show some sort of a large deformation before it actually fractures. So consider, say, a material like aluminum. It will go up and it will go something like this. This is aluminum fractured. Now for something like steel, it will go up and then come down and then go up again. This is again steel. Okay, but for say a brittle material like cast iron or wood for that matter, you can have a straight line which will become only slightly nonlinear and fracture. So what you would observe is that a ductile material like aluminum or steel has a very large strain before it actually fractures. But a brittle material like chalk, rock, cast iron and so on, they will fracture only after a very small strain, of a very small strain. Okay, so the ductility, which is measured as the length of failure minus the initial length, is very large for ductile materials and very small for brittle materials. So our subject, irrespective of whether the material is brittle or ductile, will only be focused on a relationship like this, where the relationship between stress and strain is linear. Okay, now the material, if it's ductile, will go its own path, or if the material is brittle, it may go its own path. Okay, but the whole point is we only discuss our theory in this entire course for this black region. Okay, if it's ductile, we say that our stress is such that the stress and strain are linearly related. If it's brittle, we still say that our stress is linearly related. Okay, so this region, this green region, is very small in a brittle material, and red region is very large in a ductile material, but we constrain only to the black region. Okay, so once this is clear, now so this was anyways for a so-called one-dimensional material, and there is also, I mean, if you say look at this red graph, it's because the stress which is calculated at force per area is taken as the nominal area, or which is the undeformed area. So this is called the engineering stress. If you want to calculate the true stress,
you must divide the force at the moment with the true area at that time. Okay, and this particular graph, even for a ductile material, will always be monotonically increasing. So true stress versus true strain. Okay, so strain is same. So like this one, the red one is not a monotonic graph. If you consider true strain, it will be a monotonic stress versus strain curve until fracture. It will not go up and go down at any place. Obviously, it's the engineering stress which is the initial area which is taken. Reason is it's hard to calculate measure the area while a machine is under loading. Say if there's a machine part somewhere and it's actually very complicated to keep on measuring the area at every instant of loading. Hence, this has been in fashion for a while, and I hope it continues to be the same. So for a graph like this, the linear elastic material is defined like this. The uniaxial stress is linearly related to the uniaxial strain. Okay, now that was something which you had all known, and the motivation I have clearly told you that it's enough, it's not enough. The equations or relations which we have are not enough to find the unknowns at any point in a three-dimensional solid. So the next question automatically is that what is linear elasticity in a three-dimensional solid? Meaning, we know that the stress is linearly related to the strain, but in a three-dimensional case where you have 6 components of strain, or so-called 9 components of stress and 9 components of strain, which component of stress is linearly related to which component of strain? So I'll repeat the question. Which component of stress is linearly related to which component of strain? Okay. So because there are 6 components of stress and 6 of strain, which component of stress is linearly related to which component of strain? The answer to this question is that all components of stress are linearly related to all components of strain. Let me demonstrate how that looks like. Consider the sigma 11. If this stress is linearly related to all components of strain, that would look like A1 E11 plus A2 E22, sorry, A12 plus A3 E13 plus A4 E21 plus A5 E22 plus A6 A23 plus A7 A31 plus A8 A32. I always get it wrong. I want to get it in one line. Let's try that. Sigma 11 A1 E11 plus A2 plus E23 A31 E32 plus A9 E33. Then you have sigma 2, sigma 1, 2. This stress component is also linearly related to all other components of strain. So that would be B1 E11 plus B2 E12 plus B3 E13 plus B4 E14, sorry, E21, there's no E14, plus B5 E22 plus B7 E3 okay, and similarly you would go for what, 7 more terms. Okay, yes, I know that stress and strain are symmetric, so but I'm just doing for a full 9 by 9 system. Okay, we'll use the fact about symmetry very soon. So there will be 7 more terms, and let's see what do we have over here. You have 9 on this side and 9 on this side. Okay, so it's a 9 by 9 system. So you have 9 terms of this on this side and 9 on the other side. So let's see, the symmetry of the strain tensor shows that this is the same as this. This is the same as this, and this is the same as this. Okay, what would that mean? That would mean that you can write sigma 11 is equal to a1 e11 plus a2 plus a4 e12 plus a3 plus a7 e13 plus a5 e22 plus a6 plus a8 e32 plus a9 . Okay, so you should notice now that you have now got, so a2 plus a4 can be written as another constant, say called a24. This can also be written as another constant, and this can be written as another constant. So notice now that you are only left with 6 terms on this side. 1, 2, 3, 4, 5 and 6. Okay. Similarly, this sigma 1, 2 on this side will be the same as sigma 2, 1, which is one of these 7 terms. Okay. And hence you will now be left with 6 terms on this side as well. Okay, so that is one easy way to see how this 9 by 9 system gets reduced to 6 by 6 system. The reason is because of the symmetry of strain and the symmetry of stress. Okay, so let me write out a 6 by 6 system now. That should look like, now I'll just use the X system. Okay, and sigma y. First of all, let's see how what this is. So a11 clearly will be c11. Okay, a24 will be, let me write it over here somewhere. Okay, a11 can be the same as c11. I'm using another ink. Then a24 is equal to 2 times C14. There is a reason for putting a factor of 2 over here, which we will see very soon. Okay, but for now, let's just put it like, and it's not a problem, right? You can always divide and multiply by 2 to cause it like this, to write it like this. E13 is what? It should be EXZ, and that's this one, that's 2 times of C16. EZZ is E3, C13. E68 is 32 is what? YZ. So this is 2C15, and A9 is C13. Sorry, this is C12. Okay, so this is how the 6 by 6 system can be written, and similarly you would have a relation for sigma yy where it will be C12 EX, sorry, C21 EX, C22 EY plus C23 You should have 4 more terms over here. Okay, so that would be what? Sigma z, tau xy, tau yz, and tau zx. So eventually you come up with this system where you can write your elasticity tensor in this form. So let's write the sigma x C11, C12 to C16, C21, C61. Then you have 2exy, 2eyz, 2ezx. Okay. Now the reason this factor of 2 is written, because this you can easily convert to your gamma xy system. The engineering strain concept. So this can be gamma zx. This anyways is written like this, so we don't even use that symbol gamma, I think. Okay. So that's the only reason why this factor of 2 is there, so that it's easily convertible from one form to the other. And since it was only about constants, no one cares about it so much. Okay, so the elasticity tensor here, as you see, is a 6 by 6 into 36 element system. And what does it include? It says that this every component of stress must be linearly related to every other component of strain, and that the symmetry of the stress and strain tensor is satisfied. If the symmetry of the stress and strain tensor is not actually used, then you should have this 9 by 9, which is a 81 component elasticity tensor. So that would be a 9 by 9 system. Because of the symmetry of stress and strain, we can write it like this. Okay. So this 9 by 9 system which you have over here, this can be written as a sigma ij equal to Cijkl ekl. Okay. You want to write, for example, what sigma 1 1 is, put I equal to 1, j equal to 1, and then expand this first over k and then over l. You should get this first line. Similarly, you want to say get sigma 3 2, do the honors. I mean, put I equal to 3, j equal to 2, and then again expand sum over k and first over. So each of the summation, say, over k will give you 3 terms. So there will be 3 plus 3 plus 3, 9 terms. Okay, so this is how Hooke's law is written in, or the linear elasticity is written in the 9 by 9 system. So let me just write that over here. And once you consider the symmetry of stress and strain, this can be written as something like this. Okay, so this can be E1, E2, E3, E4, E5, E6. So this is this system and this is the previous one. So for now we'll be using this, and when we discuss about anisotropic elasticity towards the end of this course, then we'll be using this form a lot. But for now, this is the thing to go for a few chapters to come. Okay, so Cijkl is a fourth order elasticity tensor. It is a tensor because it follows the transformation property which we had learned in the earlier discussions. Okay, and we'll use that quite often right now. So first thing is also a question to be sort of proved, is that this elasticity tensor has the property. It's a question, I think, from chapter 4 in the book, is to prove that Cijkl is actually equal to Cjikl, and to prove that Cijkl is equal toCijlk. How do we have to prove it? based on symmetry of stress and strain tensor. So let's see how that proof works. We know that sigma ij is equal to Cij KL EKL. Okay. Now this relationship in itself does not require the symmetry of stress and strain. Okay. So at this stage there is no symmetry. Now we can write this sigma ji is equal to Cjikl EKL. How can we write that? By interchanging I and j. Since both of them go from 1 to 3, we are interchanging I and j. That's the reason we can write this from the previous expression. We could have also interchanged I with k and k with j or L with I and so on. But that will not help us prove the property. So we are only choosing this or making this interchange since it proves this property. And you can, if you are ever in doubt how this works, well, expand this and see, expand this and see. You will get the exact same expression. So that's one easy way to convince yourself that by interchanging I and j, you are not actually changing the equation or the equations. Now, next step is to write from this one such that sigma ij is symmetric. Because sigma ij is symmetric, stress is symmetric, sigma ij is the same as sigma ji. So from coming from here to here, I have just written this expression. Jikl remains the same. Now you can use A and B, okay, to find using A and B, we get Cijkl minus Cjikl EKL equal to 0. Okay, you can just subtract A minus B. Okay, so A minus B. Now this expression, this equation which you see is valid at one point obviously, but it's valid for any arbitrary component of strain. For any value of strain this should be true. So this implies that Cijkl is equal to Cjikl, and that proves your first property. Now the way to prove the second one, which you must do, is to begin with the Hooke's law again, make suitable transformations like we have interchanges, and then use the symmetry of the strain tensor, and then you should be able to prove the second property as well. Please do it. Do not proceed ahead without doing this, because this is the only way you will understand or be sure that you have actually understood this particular derivation which we have just done. Okay, so let's continue ahead only after you have done. Okay, so this is one fascinating property about the elasticity tensor, and we'll be using them quite often later on. There is another property which will come up for us only after studying strain energy density, and we'll do that at the right time. So for now, let's somewhat summarize. We had an elasticity tensor which had 81 components. Again, it is a tensor because it does satisfy the transformation property which we have learned. The 81 components were reduced to 36 components. Okay, this was because of the symmetry of the stress and the strain. This 36 will be reduced to 21 independent constants. This will happen when we learn about the strain energy density. So I am just telling you what is about to come. This was because the stress and strain were symmetric. And this will move on to some other reductions before being told that for an isotropic solid, and I'll tell you the meaning of isotropy in a moment. this you will have only two independent constants in the elasticity tensor. Okay, so this will come out in more detail in when we study anisotropic elasticity, but for now you should remember that an isotropic solid, if following linear elasticity, will have only two independent constants. A general linear elastic solid will have 36 independent components provided uh, the stress and strain is symmetric. It will obviously be reduced to 21 in the future discussions, and we'll see where that happens. But for now, this is the sort of timeline, not the timeline, but the reductions of how it happens. Now, there are two more things which we must learn now. One is about the homogeneity, or the so-called material homogeneity, and the other is isotropy. For the entire course which we are learning, both the material must be homogeneous and isotropic. So let's take it one step at a time. A material homogeneity means that the elasticity tensor, okay, or Cij, whichever way you would want to call it. This is in the 9 by 9 format, the other is in the 6 by 6 format. Both of them are space independent, meaning they do not differ from point to point. So if this is your solid, if there is stress and there was strain and there is stress, the relationship between them will be such that sigma ij is equal to Cijkl ekl at this point. Okay, so the relationship will be there. Now if you take any other point, this Cijkl will remain the same. Of course, the stress and strain can be different. If strain is different, the stress will definitely be different for the same Cijkl. So that's the idea, that Cijkl is constant with space. Anywhere you go, you will get the same Cijkl. That's a homogeneous material homogeneity. Many a times it is there in the material, many a times it's not there, and it can be assumed. And there are certain cases like composites where it can not be assumed at the microscopic scale. For example, if you have, say, a solid like this which has reinforced steel balls like this, so clearly the Cijkl in these parts will be very different from the bulk. Okay, so if your point of interest is lying over here, the Cijkl will be different. If your point of interest is lying over here or here, the Cijkl will be different. So this is the concept of homogeneity, and in our case, as I have said, Cijkl will not be changing. You can have some other artificial materials be made in which, say, the Cijkl varies with time, varies with space. So if your x-axis is like in this direction, okay, you can have a situation in which Cijkl is equal to Cijkl naught 1 plus alpha x. So as you keep on going up in the x direction, Cijkl will keep on increasing depending on what alpha is, okay, increasing or decreasing. So this is a functionally graded material, clearly non-homogeneous, okay, and many a times in aerospace or automotive industries, these materials are artificially made so that you can define how the elastic properties vary with space. Okay, so you can also have this. So I'm only taking one dimension, but I hope you can see that both x, y, and even z can come. Okay, so if the elastic properties vary exponentially, this is how it looks like. Okay, so this is how the homogeneity can be explained, and our material has to be homogeneous, meaning Cijkl at every point in the solid will be same. Obviously the strains can be different at this point and at this point, and hence the stress will be different because of this Hooke's law, but Cijkl will be the same. The second concept is isotropy. So isotropy is that the material response is different along different direction. That's anisotropy, and the material response is independent of direction. That's isotropy. So let's consider two small examples, actually one example but two separate tests. If you consider a piece of foam, the spongy foam which you can perhaps find in your kitchen for washing utensils, and then put a steel, then put another foam, then put another steel, and so on. Okay, now make two such things, foam, everything else remaining the same. Conduct this test. Apply the same stress over the top, sigma y, and try to measure how much strain has happened. Do the same over here. Apply the same stress. Let me just call like this. One, two, three. Foam S, foam S. Conduct this sigma y over this entire area, obviously, just like this was over this entire, hence we are taking it as sigma y, and this should be sigma x, and calculate how much strain has happened in the x direction. Now, if sigma x is the same as sigma y in value, what do you think would be the deformation relation? Will epsilon y be greater or epsilon x be greater? So as you may have guessed, in this case, because of the foam, epsilon y will be greater. Epsilon x will be lesser, because even though the foam may allow easily to be compressed in the x direction, but the steel will not allow such a free compression. And hence, since we have to consider this entire boundary straight, we have to conclude that the compression in this x direction will be less compared to y if the same magnitude of stress is applied in both the cases. Okay, so that would mean that this overall material which we have made responds differently when you apply the same load in the y direction, and it responds differently when you apply the same load in the x direction. Okay, and hence this is a anisotropic material. Okay, for this case, the Young's modulus would be in the y direction would be sigma y by epsilon y, and Ex is equal to sigma x by epsilon x. So since this and this are the same, okay, now epsilon y is greater than epsilon x, this implies that Ex is greater than Ey. So the so-called Young's modulus in the two directions are different, and that is the meaning of anisotropy. This is only not limited to this. You can have a material, say for example, the material like this, which allows the electricity to pass much easily in this direction compared to this direction. Okay, you can also have a material which allows light to pass freely in this direction, but not so much or not at all in this direction. So this is also an anisotropy in the optical and the electrical properties of the material. Here we are obviously concerned only about the mechanical response, and hence the answer that Ex is greater than Ey in this case. Now consider this for an isotropic, say a tennis ball or a squash ball. You apply a force in this direction, the deformation along this line will be the same if you apply a deformation in this direction or apply a load in this direction. So such behavior, if for the same material you are getting the same deformation in along any direction, is called isotropy, and hence the mechanical response of this is independent of the direction where you are considering. So we have discussed that our material has to be homogeneous and isotropic for the discussion ahead. Okay, so for this course this is the case, but I think you have learned it well enough so that you can actually extend it if ever the need comes for that. Okay, so this is where we are right now, and let's now take up a call of what an isotropic material looks like and what should be CIJKL. Okay, for an isotropic material, what should be or what form of CIJKL should be there. So let's do that, and we'll have to do a certain examples before this to actually understand what isotropy is. So one of the first things which we had learned was that isotropic tensor does not transform under an arbitrary transformation law. Just like a scalar quantity, for example, if it's 200 centigrade, it will remain 200 centigrade under any transformation. Okay, and hence it must remain independent of the coordinate system. So the same must be the definition of a isotropic tensor. CIJKL, as we are telling, we are trying to make it a isotropic tensor, but let's start with an easier tensor and see how that works. So this is a question from chapter 1. It says that show that the second order tensor A delta ij is isotropic. What isotropic means? It retains its form under any transformation. This is the most important part. Only thing is they have to be a orthogonal transformation, meaning the x, y and the x dash, y dash are perpendicular to each other. So that's something which we anyways do in our study. And this is A delta ij is an isotropic second order tensor if we are able to prove that. So let's see how this proof works. For any tensor, because it is a tensor, it must follow the transformation law, which is QPI QJ AIJ. Okay, AIJ is already given to us as A delta ij. A is an arbitrary constant. Now A dash PQ is QPI QQJ and A delta ij. This is written as AQPI QQJ delta ij. This particular thing can be written as a QI. The reason this can happen, two ways. One is that you can expand and see. I think we had also done a property about this. And the other way, since we have somewhat advanced in this course, is to say that of course this will be a repetition over J, and the only terms which will actually contribute are the case where J is equal to I. Okay, every other term will be 0. So an easy way is to write it as QQI. Just replace this J with I. Okay, so that's one way, and also the property which we had learned and I think seen the proof as well before. So that's something which we have already done. Now you want to write that A dash PQ is AQPI and QQI. This particular thing has been written as delta PQ. for an orthogonal transformation, it satisfies the property of QPI QQI is equal to delta PQ. We have already gone through this discussion. If you do not recall it, please go back and check, since it's very important to be clear of every step which we are making. Okay, and now this can be said, I mean, just replacing A with P with I and Q with J. Okay, so this is how it looks like, and as you see, the transformed tensor is the same as the original tensor, and hence it did not, the form was retained in under any transformation. The only condition was that it should be an orthogonal transformation, which anyways is true even from the start for this course. Okay, so if xy is like this, the new x dash and y dash would still be 90 degrees. So the orthogonal transformations, this is true. Okay, so the form is retained, hence A delta ij is a isotropic second order tensor. Now we will somewhat advance because our elasticity tensor is a fourth order tensor. So there is a very standard form which was given in literature for a fourth order isotropic tensor, and people would want to use it in the theories. So that form is given as say Cijkl is equal to alpha delta ij delta kl plus beta delta ik delta jl plus gamma delta il delta jk. We have to show that this is the isotropic fourth order tensor. So for isotropy, what will happen? Under any transformation, it will retain its form. So let's see how that works. So we have to first put this, and this is also a question from chapter 1, by the way, just at the back of the chapter 1 you have this. So let's first write the transformation law, and that can be Aijkl dash is equal to Qip Qjq Qkr ls APQRS. Okay, now if we want to, so this is the so-called old fourth order tensor, and this is the transformed value. So we want to write it as APQRS. We want to write this given form as APQRS. So what would that be? APQRS is equal to alpha delta PQ delta RS plus beta delta PR delta QS plus gamma delta PS delta QR. Now we want to plug this in over here. Sorry, this should be QIP QJQ QKR alpha delta PQ delta RS plus beta delta PR delta QS plus gamma delta PS delta QR. Okay, so now let's see how this can be done. I will only do for one term since it will otherwise become very lengthy, but you must do for all three. So let me take the first term, alpha QIP delta PQ QJQ QKR delta RS. So writing these terms in the way I am writing requires some sort of experience through learning this subject, and that will happen in due course. Plus there is a beta term not writing, there is a gamma term not writing. Okay, let's see how some commonalities can definitely be done. Okay, so let's put out this as alpha, and QIP delta PQ. This would work only when P is equal to Q. Every other term will be equal to 0. So you have this, and then this term would work only when R is equal to S, plus the beta term plus the gamma term. Now again look at both of them. This would look like alpha delta ij delta kl, plus not writing the beta term, but that would come out to be delta ik delta jl plus gamma delta il delta jk. Okay, a dash I j k l. Okay, so as you can see, this transformed aijkl looks exactly like the one which was given to us over here. Okay, and hence this is a isotropic fourth order tensor because it retains its form under any general transformation. And this property, just to remind you, was because for an orthogonal transformation, this property holds. Okay, so looking at this, it was given, and which we will follow, that Cijkl, if it is a elastic tensor, which is a fourth order elasticity tensor, it must follow this for isotropy. Okay, this particular form we will keep. So alpha, beta and gamma are arbitrary constants, and we want to now write the Hooke's law for an isotropic solid. So Hooke's law is like a linear elasticity itself, but now you want to add an isotropy as well. So let's see how we can do that. We have sigma ij equal to Cijkl ekl. Okay, this is linear elasticity. This does not know anything about isotropy as of yet, but as soon as you put this form of Cijkl inside it, then clearly the material will be elastic other than being linear elastic. So let's do that. Alpha delta ij delta kl ekl plus beta delta ik delta jl ekl plus gamma delta il delta jk ekl. Okay, so now let's look at this term. Let's look at this term, and let's look at this term. Okay, so let's go one step at a time. For this to be true, L has to be, for non-zero terms, L has to be equal to K. So we'll just write it as EKK. Okay, for non-zero term, for this red bracket, the second red bracket which you see, L will have to be equal to J. So this should be written as E
uh, sorry, L will have to be equal to J, so it will be written as EKJ. Yes, and then for the last one, you will have delta IL. Uh, K will have to be equal to J, so it will again be JL. Okay, now again look at this and this. So this would be sigma ij equal to sigma ij alpha. It will remain alpha delta ij ekk just because there is no repeated term over here. Okay, so for this, the non-zero terms, k will have to be equal to I, so it will be ij. For this non-zero term, L will have to be equal to I, so that would be ji. This can be written as alpha delta ij ekk plus beta eij plus gamma eij, because eij is the same as eji. Strain is symmetric. This implies that this is alpha delta ij ekk plus beta plus gamma into eij. Okay, so this form which you see over here can be written as sigma ij is equal to lambda ekk delta ij plus 2 mu eij. This is the Hooke's law for an isotropic solid. Okay, as you see, there are only two independent constants, lambda and mu. Lambda is called the Lame parameter, and mu is the shear modulus or the modulus of rigidity. Okay, it was possible because beta plus gamma, which were arbitrary constants, can be combined together to write another constant, which is 2 mu. Okay, and alpha has been written as lambda. Okay, so lambda and mu are constants, and they are the two independent components of the isotropic elasticity tensor. Okay, so this can obviously be written in the expanded form. If you want to say write what sigma 1 1 is, you have to put I equal to 1 and j equal to 1 and write this. Similarly, you can write it in the x form. So let me do one of it. I equal to 1, j equal to 1 will give me sigma 1 1 equal to lambda e11 plus e22 plus e33. Okay, and delta ij will be 1 plus 2 mu e12. This can also be written in the xy system as sigma x equal to lambda ex plus ey plus ez plus 2 mu e, sorry, yeah, this should be ex e11 because I and j both were equal to 1. Okay, so this is how it can be written in the x form. Similarly, if one wants to write sigma y, they should choose sigma 2 2 and I equal to 2, j equal to 2, and so on. So this would look like sigma y is equal to lambda ex plus ey plus ez plus 2 mu ey. Ez is equal to lambda ex plus ey plus ez plus 2 mu ez. And tau okay, so this is called the generalized Hooke's law, either this expanded form or this shorthand form. These are called the generalized Hooke's law for a linear elastic isotropic material. Okay, so the isotropy is coming in because we chose a particular form of CIJKL. Okay, now we have seen that there are always two independent constants, parameters in the elasticity tensor. Now, if we want to sort of invert this, okay, meaning you want to write the strain in terms of stress. So this is if you have strains given, you can find the stress at a point.
where the material is linear elastic isotropic. If you have the reverse given, in the sense you have the stress given, stress components given at any point, stress is given at any point, how would you find the strain? Okay, so you have to find stress is equal to something in terms of stress, strain is equal to something in terms of stress. So let's do that once and see. So let's start with the, so this is called inversion, by the way, you should know this name. So you have sigma ij is equal to lambda e k k delta ij plus 2 mu e ij, and you want to find eij is equal to what? So the first step is called contraction. Put I is equal to j equal to k, or you just put, don't want to confuse with a k, just put a p. Okay, so sigma pp is equal to lambda e k k delta pp plus 2 mu e pp. This would imply that sigma pp is equal to lambda 3 lambda e k k, because delta pp is equal to 3 plus 2 mu e pp. Now EPP and EKK are the same, in the sense both P and K go from 1 to 3, so they can be interchangeably used. So I'll write it as sigma KK. Sigma KK is equal to 3 lambda plus 2 mu EKK. This implies EKK is equal to sigma KK by okay. Now what we want to do is we want to substitute this EKK over here. Let's see what we get. Sigma ij is equal to lambda sigma kk by 3 lambda plus delta ij is plus 2 mu eij. Now we want to write eij is equal to sigma ij 1 by 2 mu sigma ij minus lambda by 3 lambda plus 2 mu sigma kk delta ij. Okay, so this form I think is the largest form. The sort of, it cannot be simplified any further. So again we come back to this. If you had any given point, you had sigma ij given, now you can find the strain at the same point if the material was linear elastic and isotropic, since you have lambda and mu over there. This can also be written in a form which is somewhat more convenient to us, and that is 1 plus nu by E sigma ij minus nu by E sigma kk delta ij. This will happen when you write E is equal to mu 3 lambda plus 2 mu by lambda plus mu. This is called the Young's modulus E, and you can call nu as lambda by 2 by lambda plus mu. This is called the Poisson's ratio. Okay, so this are the two forms of writing this. As I've said, for the inverse Hooke's law, this form in terms of Young's modulus and Poisson's ratio is more convenient, and we'll be using that if we ever have to use the inverse Hooke's law, which is very soon when we learn about thermoelasticity. But yeah, so one of the things is that though you see all these symbols of E, nu, lambda, and mu, independent are only two. Okay, that fact does not change. Since you have these relations already, okay, you can clearly see that you have only two independent constants. Now if you want to write this in the expanded or the xy form, just proceed in the same manner. If you want to write ex or e11, just put I equal to 1 and j equal to 1 and work around this. So ex would come out to be 1 by e sigma x minus gamma sigma y plus sigma z. You do not have to remember these expressions, okay? All you have to do is remember the steps and the reasoning behind what we are doing. Then you also have the shear terms. Exy, how would this come? Put I equal to 1 and j equal to 2 in this one. You should get 1 plus mu by E tau xy equal to 1 by 2 mu tau xy. Yz will be equal to 1 plus nu by E tau yz equal to 1 by 2 mu tau yz. E zx is equal to okay. So this is the inverse Hooke's law, and in the discussions to follow, we'll be learning about what is the physical meaning of these elastic constants which we are learning, like E and nu and so on. Okay, we'll try to learn about that, and then finally we'll be moving to the thermoelasticity, which is basically the loading is mechanical plus thermal. So how does linear elasticity work then when you have both mechanical and thermal effects? Okay. Okay. So in our pursuit to find the relationship between stress and strain for a linear elastic isotropic material, we have introduced certain constants. There were lambda mu, there were E nu, and we now want to understand what is their physical meaning. So that's the agenda for today, because for us they have just been some sort of a parameter or an arbitrary constant and whatever you would want to call it, but we would want to now attach a physical meaning to those elastic moduli. So let's proceed in that direction. So this we can call as physical. Okay. So there are certain tests which we can do in a laboratory, okay, and we try to understand the meaning of these elastic moduli through these tests. So this is a so-called simple tension test where you create a dog bone structure. The idea is that whatever failure has to happen should happen in this region, okay, not where the clamping is done. So if you have, say, an element like this, it would experience sigma in this form. Okay, now if you have a simple tension test as is shown, okay, and the direction is x, okay, so I mean the sigma is in the x direction, then the state of stress is represented by this situation, meaning at this point this is the state of state which should exist, sigma 0 0 0, 0, 0, and 0, 0, 0. Okay. Now, once this is done, using the Hooke's law, we should be able to find the strain components as well, or the state of strain. Okay. So let's see how that can be done. So how do you find the stress from the strain? So remember we had this, so strain from the stress, remember this we had derived. Okay. So once you substitute this, for example, to find Eij, you need certain terms, say E11. So that will be 1 plus nu by E sigma 11 minus nu by E. Sigma kk is the summation of all the diagonal elements, that would be sigma, and delta ij is 1. Okay, so this would be 1 plus nu by E sigma, because sigma 11 is sigma, minus nu by E sigma. This would be sigma by E. Okay, so this would be sigma by E. Similarly, you can find all the other 9 terms, so most of them are 0. This would be okay. So just for example, if you had to find this, which is E23, you should put I equal to 2 and j equal to 3 in this, and then find this value. Okay. Okay, so this is the state of strain which we have received at this point of interest. Again, this point of interest. Now E therefore is sigma by Ex. Okay, this value is Ex. And that's the slope of the stress strain curve. Okay, so if you draw for a uniaxial test sigma by Ex, this slope would be E. So that's the physical meaning of Young's modulus or elasticity modulus. Now you look at the other term, which is nu is equal to minus of Ey by Ex. Okay, so you can find the relationship. So this was Ey, if you remember, and this is similarly equal to minus Ez by Ex. So this is the nu is the negative ratio of transverse strain to axial strain. Okay, both y and z are the transverse strain and x is the axial strain. So this is something which you can remember. Both of these things you should remember. Okay, that the Poisson's ratio is the negative ratio of the transverse strain to the axial strain. Okay, so the importance of this test, a simple tension test, is that using this one test you can find the elastic constant E and nu. Okay, both of E and nu can be found out, and as you know, once you find out these two properties, this is the only two independent constants for an elastic isotropic material, and hence now you can use these properties in any sort of complicated test or situation which you want. So this is used to characterize the material. You say that these are the elastic properties of this particular material. Okay, fine. So that was the so-called first part. Now let's try to look at another test, which is for a round sort of cylindrical specimen like this, and you are twisting it. So this double arrow which is there, it shows that you are not actually pulling it but twisting it. This is a convention which is very clearly known, and it's just like if you hold a pen from one hand and try to twist it from the other hand, other fingers, this is the same sort of a loading which you apply. And this is called a pure shear situation, in which you would have a tau, you would have a tau, you would have a tau, and tau. Okay. Compare this to the simple tension. You only had sigma in the x direction and minus sigma in the other, and that was there for the equilibrium of this element which we had. Similarly, we also want an equilibrium for this one, and this is a pure shear, so there is no normal component. Okay. Now this is the definition for a thin walled cylinder. The importance of this word thin walled will be coming up later. Okay, but for now you should just take it without knowing the reason for this. The thin walled cylinder is subjected to a torsional loading, meaning twisting moments are applied, and then the state of stress in this situation for the same sort of this point in the center of this element over here, that can be represented by 0 tau 0 tau 0 0 and nothing in the z part. Okay, now you can again apply the Hooke's law, this particular relation, in the same way as you had done before, and find the strain at this point of interest. So that would be the state of strain, the so-called by 2 mu equal to 0 tau by 2 mu 0 0 0 0 0. Okay, so we have found out this value. Now it is easily observable that mu in this case will be equal to tau by 2exy, or tau is equal to gamma xy, the engineering strain. Okay, so this modulus is just the shear modulus is just the slope of shear stress strain curve. So if you had a tau and gamma xy, this slope is mu. Okay, so this is the physical meaning of the shear modulus. Now let's virtually conduct another test, and that's a simple hydrostatic compression. This is the same kind of a loading which an element would have, a solid would experience if it is immersed in a liquid. So you would have pressure from all the three sides. Okay, this is called a hydrostatic compression. If a solid, for example, a piece of rock is buried deep inside the earth, okay, a few 100 meters below the earth, then it would also experience a similar force. Then it would be called a lithostatic compression. Okay, litho word for the earth, but it's the exact same idea. Now this is also a hydrostatic compression or a tension. I mean, you can also apply a tension force. It's just that it's easier to perform this, and civil engineers have a very nice way to do these tests. What they do is they put up a piece of rock sample and then surround it by oil from all sides, and then they apply the loading so that the pressure generated in the oil is then applied to these rock pieces. So they call it a triaxial loading, meaning this load is applied on all the three axes. So you have to choose a suitable geometry of the specimen, but the ideas remain the same. Okay, so this is about a uniform compression or tension in a cubical specimen. So we are concerned with the cubical specimen only, and the state of stress in this case can be written as sigma ij is equal to minus p 0 0 0 minus p 0 0 0 minus p, and this is equal to minus p delta ij. Okay, because you can just write this minus 1 0 0 0 minus 1 0 and 0 0 minus 1 as minus delta ij. Again, I mean, just using the inverse of the Hooke's law, which we have been using in the earlier two cases, we can write it as 1 minus 2 nu by E. Please do this, okay? Do not leave this out. Try to find that the strain field is actually equal to this. Okay. So this is the strain field which you would get at the same point, I mean the center perhaps of this element. Okay. So let's see if we can physically interpret this. Before doing that, I think we should first do a question from chapter 2 in the textbook. Okay. And we'll come back to this later on. So this is a question from the second chapter. It says a rectangular parallelopiped okay with original volume V naught is oriented such that its edges are parallel to the principal directions as shown in the figure. So let me just show the figure itself first. You have one, sorry. So the original volume of this is V naught, okay, and it is oriented such that its edges are parallel to the principal direction. So 1 2 3 are the principal directions, and it's shown to us. Now for the small strains, we have to show that the dilatation, okay, or let me use some other fancy expression. Okay, so this is EKK is equal to change in volume, which is delta V by original volume. So this is something which we have to show. So the dilatation is the change in volume divided by the original volume. So let's see how we can do that. That's the answer or solution. It's the best way. I think it will be quite complicated for me to draw this, so I'll just do something like this. Okay. Now let the volume of this element, the original volume as you know, be, I don't know, dx1 dx2 into dx3, assuming that each of these sides, like this is dx1, this is dx2, and this is dx3. Okay, so this is the original volume, and now we say that after deformation the new volume would be 1 plus e11 dx1, 1 plus e22 dx2. Okay, this has become now 1 plus e11 dx1, and this has become 1 plus e22 dx2, and the third axis, this side, has become 1 plus E33 dx3. Now this has happened because the coordinate system here is along with the principal directions. So we can easily write that the change of length in side 1 is this, change of also the total final length is of side 2 is this, and final length of side 3 is this. If this was not in the principal system, we wouldn't be able to write it like this. Okay, so let's expand this. That would be dx1 dx2 dx3 plus e11 plus e22 plus e33 dx1 dx2 dx3, and then there are the other terms which are the square of strains. Okay, meaning for example it can be e11 e11 e22. Okay, so terms like this and many more. So we are writing it as higher order terms. This we can approximate as dx1 dx2 dx3 plus e11 plus e22 plus e33 dx1 dx2 dx3 because of small deformation. So the higher order terms can be removed because the strains are assumed to be small, and this would imply that Vf is equal to V naught into 1 plus EKK. Okay. Now the change in volume delta V will be equal to Vf minus V naught, and that would be V naught EKK, and hence the dilatation, which was defined as delta V by V naught, will be equal to EKK. So it is now proved. So the dilatation represents the change in the volume with respect to the original volume, and this is given by EKK. Okay, that's the first thing which you should know. Now, can we use it for an element which is not actually inclined? Sorry. Okay, can we use it for an element which is not inclined along the coordinate axis? The answer is actually yes, because this, if you recall, is a invariant, meaning this value ekk, which is the summation of the diagonal elements, will not change depending on the transformation which this tensor has gone through, and hence this dilatation should remain the same even if the system is not a principal system. Okay, now let's come back to where we were. So we had found out the state of strain at this point of interest using the inverse Hooke's law, and we want to now write the dilatation. That would be ekk, and that would be minus of 3 times 1 minus 2 nu by E by P. Okay, or this can be written as P is equal to minus kappa V. Okay, and K, as you know, will be equal to what? E minus, or okay, so K kappa can be equal to E by 3 1 minus 2 nu by P by, okay, sorry, not P, okay, yes, so that would be kappa, and this is called the bulk modulus. So this is also a property which we require, and what you see is bulk modulus is somewhat of a ratio, negative ratio between the pressure applied in a hydrostatic compression by the dilatation. It also physically represents the ratio of the pressure to the dilatation. So as you see, kappa represents the ratio of pressure to the dilatation. And the Poisson's ratio, so let's see, if the Poisson's ratio in this expression approaches 0.5, okay, the bulk modulus kappa tends to infinity. Can you see that in this expression? If the Poisson's ratio becomes or tends to 0.5, the bulk modulus tends to infinity. Okay, this physically implies that it is incompressible, meaning you will not be able to, I mean, to cause kappa tending to infinity, uh, this dilatation has to be very small, and hence that small that it is actually incompressible. So this is the physical meaning of this statement, that if the Young's modulus approaches to 0.5, kappa has to tend to infinity. Another way to look at it, if it is a compressible solid, in the sense if it will deform, then the Poisson's ratio cannot be greater than 0.5. Even at 0.5 it's not possible, so it has to be less than 0.5 if the solid is to be compressible. Okay, so what we have is that we have introduced many elastic constants. Of course, only two of them are relevant. Okay, two of them are independent. Others can be derived one way or the other. So if you look at table 4.1, you will have the say E and nu in terms of E, that will be E. In terms of nu, this will be nu. In terms of kappa, this will be E by 3 into 1 minus 2 nu. Okay, and mu will be equal to E by 2 1 plus nu, and lambda will be equal to E nu 1 plus nu 1 minus 2 nu. Okay, so all possible combinations are there, so you can check out this textbook and so on. Okay, similarly you have table 4.2, which gives the properties of these elastic modulus. For example, for aluminum, E in GPa is given as 68.9, nu is given as 0.34, mu is given as in GPa as 25.7, and you have the thermal coefficient of thermal expansion as this. Okay, so test 25.5. So for some other materials as well it is given. You also have it for rubber. Young's modulus is 0.0019. The Poisson's ratio is 0.499. That tells a lot about what this should be. Okay, please think about it and convince yourself what this value of 0.499 nu means. The Poisson's ratio being 0.499. Remember, we have just discussed it. Okay, and then you can also have it for steel and other materials. So you, for any material which can be classified as a linear elastic isotropy, all these properties would be available in some data book or the other. Okay, so you have now seen the physical meaning of these elastic constants. The next and perhaps the last topic which we want to discuss under this heading is called thermoelastic constitutive relation. Okay, so first I would try to motivate why we are learning this, and then we'll actually see how the mathematics of it looks like. So we know that if you have a change in temperature, and if the solid is allowed to expand or contract freely, meaning you have an unrestrained elastic solid, then the deformations will automatically change. The dimensions would change, the deformations would happen, and as soon as deformation happens, we have to quantify that deformation, and you would have the quantity strain over there. Okay, so this is what would happen. And in a general situation where both mechanical and thermal loadings are applied, I mean, you are applying, say, a force on the boundary and the temperature is also either increasing or decreasing. In that case, you will have the strain due to both mechanical and thermal effects. Okay, so that's the first statement. A general strain field results from both effects. Remember, all this is only true for an unrestrained solid, meaning the solid is allowed to expand or contract. If it's a restrained solid, then the effects are somewhat different. So let's see. Now, in the context of small deformation theory, linear elasticity will happen, and in that case, the total strain can be written as a summation of mechanical plus thermal effects. Okay. All this while we have been only learning about the mechanical strain and stresses, and you will have the thermal effects additionally because of this general loading. The two strains at any point, again, all this is only valid at any given point. Okay, Eij is equal to Eijm plus Eijt. So at any given point on this elastic solid, under a so-called thermomechanical condition, the strain can be added because it's a small deformation theory. So both the components are small and hence it can be added. Now, so we want the reference temperature to be called as T naught and the final temperature be T. Okay, so basically the thermal effects are adding such that the initial temperature was T naught and the final temperature is T. In this situation, the thermal strain from our earlier knowledge can be written as alpha ij T minus T naught. Okay, where alpha ij is the coefficient of thermal expansion tensor. Okay, again, as soon as we call it a tensor, we know that it follows the transformation law of a tensor, and alpha ij is clearly can have these 9 components. Okay, so alpha 11, alpha 12, and so on. And we have already seen that if alpha ij is isotropic, it must have the form alpha delta ij. We have done this question and proof with us. It's isotropic because under any uh, general transformation, it will retain its same form. So if alpha ij is isotropic, that's our assumption. Okay, because we are working with linear elastic isotropic materials, so why to introduce anisotropy in thermal effects as well? So we should have a linear elastic isotropic solid, and the isotropy exists both in thermal and mechanical effects. So that's what we are doing. Of course, in the more general case, it will be anisotropic, but we want to constrain ourselves to a simple case. So we put it over here and then write as alpha T minus T naught, the final temperature minus the reference initial temperature, and this is the thermal effect. Now obviously we have this table which we have just discussed, 4.2, that gives you the values of alpha. Okay, for aluminum it was 25.5 into 10 raised to the power minus 6 per degree Celsius, and for rubber it is 200 into 10 to the power of minus 6 per degree Celsius, and so on. So that's there. Now we want, for isotropic materials, we want to just like add. So let's see, we want to add the mechanical effects and the thermal effects. So the inverse Hooke's law which we had derived was the mechanical strain. So we'll first write that. Okay, so this is the mechanical strain, this is the thermal strain, and isotropy is there both in mechanical and in thermal. And now we want to invert this to find the stress at this point, due to both mechanical and thermal effects. So the strain is easily found out by just adding, because both of them are small. We want to now find out the stress due to the thermal and mechanical effects. So let's see how we can do that. We want to now use the concept of contraction, in which case we have to do this. So let's see if there is a there is some note in our study. Okay, okay, so I think we should now make that attempt. Let's see how that can happen. Mhm. So let me just use some other ink. So the final expression which we want to have, let's see, let's put I equal to j equal to p in this one. Okay, just like we had done earlier. So that would be epp 1 plus nu by e sigma pp minus nu by e sigma kk, and then delta pp plus alpha t minus t naught delta pp. Okay, this value is 3, this value is 3, so epp can be written as 1 plus nu by e sigma pp minus, okay, so this should give us, I think this also we can write it as, so since now it's only k and p, we can just replace this by k, and we can replace this by k. Okay, so this should be written as ekk is equal to sigma kk 1 minus 2 nu by e plus 3 alpha
t minus t naught. Now, what should we substitute? We want to put sigma kk from over here to in this one. So that should give us Eij equal to 1 plus nu by E sigma ij minus E by this expression should be ekk minus 3 alpha t minus t naught by 1 minus 2 nu by E plus alpha t minus t naught delta ij. We just check. Okay, Eij is equal to 1 plus E 1 plus nu by E sigma ij minus nu by E sigma kk is ekk sigma kk is ekk minus 300 by 2 nu by E. Okay, plus okay, so now we can take sigma ij on one side, and that we should be able to write out sigma ijj will be equal to, so we should write 1 plus nu by E sigma ij. This is equal to Eij minus alpha t by t naught delta ij plus nu by E delta ij ekk minus 3 alpha t minus t naught 1 minus 2 nu. Okay, 1 plus equal to Aj minus and then plus this. Okay, so it seems we are getting close, and then this should imply that sigma ij is equal to E by 1 plus nu Eij minus alpha t minus t naught delta ij plus nu by E delta ij ekk minus 3 alpha t minus t naught 1 minus 2 nu. Okay, fine. So now let's replace this by some sort of other constants. Let's see. E, this should be Eij 1 by 1 plus nu Eij. This should be E by 1 plus nu delta t minus t naught delta ij plus nu by 1 plus nu delta ij ekk minus 3 alpha t minus t naught. Okay, and this should be 1 minus 2 nu. E by 1 plus nu Eij minus E by 1 plus nu alpha t minus t naught delta ij plus nu by 1 plus nu 1 minus 2 nu ekk delta ij. Okay. Okay, so far so good.
Let's see if we can reduce some of them. E by 1 plus nu can be written as 2 mu. Okay, so this can be written as 2 mu. Okay, that's the first step. Let's see what else can we do. Then we have this particular term. Let's see this. So nu, this particular term, nu by 1 plus nu, 1 minus 2 nu. Okay, this can be called as, I think, let's no, not something. So we are trying to check the table just for your information. Okay, we have to try this, or let me do this. Let me just write out the final expression. I think that part should be done by you. Okay, so you should check the table and try to reduce this. So I'll put this as how. Okay, you should be able to reduce it to this form. So this is the stress at the point of interest due to both mechanical and thermal effects. Okay, so you should be able to do this, and if you are not, please don't hesitate to ask me. So this is the isotropic case, and isotropy here exists in both mechanical and thermal effects. That's the important part. Otherwise, you would have to take it as alpha ij without simplifying to alpha delta ij. Okay, so this finishes our discussion on linear elasticity and thermal elasticity, linear elasticity and thermoelastic effects. And now we'll be next moving on to the boundary value problem and formulating the problem as such, and then learning some methods to solve it. So that would be our next thing, next topic. Thank you.